post that on the website?
Yeah, I'll do it also. I can do it also.
Okay.
It actually will show. The YouTube will actually show. Now you can actually click on it.
Where?
Oh yes, there's live and it's on YouTube and it's recording.
Where does? Okay, I don't see this, but okay.
Yes, I see live on YouTube, through YouTube and recording.
Okay. So anyway,
so we're on air.
let's go for it. So I just want to welcome all you guys to the conference and remind you a couple of things. One of which is that it's really important that you register because if we get Zoom bombed or there's an issue, we're going to have to shut down the session and restart with a passworded session. And so that's why we talk about rapid and urgent communication. But also I checked last night, at least one of my emails sent out for the conference mailing list went into spam filters. So if you can't find the email or the email with the new Zoom meeting ID and password, don't scream at me initially, check your spam filter. Okay, there's a program change on Wednesday morning. It's fairly self-evident what that's about. So we will not be having a morning lecture. The other sort of two pieces of etiquette. Basically, if the dog runs by barking and your microphone isn't muted, we'll get to see you and perhaps the dog. Please keep the microphone muted if you're not speaking, but if you're speaking, obviously unmute it. And also, as a courtesy to the speaker, I think it's nice if you turn on your video too. At least it gives some kind of personal. You don't have to. In fact, I think it's illegal to require it, but it's just a nice piece of etiquette that you show your face when you're asking a question. So with that, I want to add one more thing, which is this was originally envisaged as a conference this week and a workshop next week, and of course to have it actually physically at Saclay. So we're planning on doing it next year in exactly that format, pretty much this time. It's the week before, it'll be the 2 weeks before Strings, which is in Sao Paulo. So we're planning on having an in-person physical conference in Saclay on June 7th, the 11th. And then followed by a shorter, similar length, but more intense workshop the following week. So to which you're all invited. Anyway, without further ado, I'm going to shut up and let Bert take over the screen. And we welcome Bert's first talk, but basically he's going to be keeping us honest on the subject of what you might actually see from black holes.
Okay, thank you. Let me see if I can get this to work, right? Do you want to continue? Yes.
There's a green button, share screen, click.
Excellent.
And just play the...
Yes. Do you see it full screen and all?
Yep. Perfect.
Okay. Well, thank you very much for, well, I guess it's for the honor of being the first to speak this week. Normally, I would also say I'm very happy to be here, but I'm a bit confused as to I don't really know what here means, being at home and all. So I want to talk a bit about connections, some fun we've been having. We're thinking about how gravitational waves and echoes, in particular, are related to microstates and ADS-CFT. And there was a question that Nick asked me in one of the emails he sent. I think it was one of the emails where he was asking for a title. And he was hoping, I think it was, that I would add a dose of reality. Well, I'm not sure what he meant by that, but let me see what I understand is that I'm interested also in understanding what these black holes, their microstates, etc., how they behave, what they look like from the point of view of an asymptotically flat observer. And in this talk, I just want to go a bit in detail on one of the observables that you can do using gravitational waves. Well, actually, I will cheat. I will just do scalar wave packets in a particular way. And that's also related to a lot of recent work that's going on in this black hole microstate geometry literature. Okay. How will I do this for you? In 3 stages. I will give an introduction, a bit of gravitational wave echo background, and then some let's say philosophical side remarks that motivate more research. I will, in this talk, in the second part, I will not sorry, I'm seeing things happening in the chat. Oh, okay. Yes, by the way, this is a question to the organizers. How do I manage questions?
We'll ask, people can unmute the microphone and they can,
Okay.
they can just
And they
ask.
can just interrupt me at any point.
At this point, yes.
Okay,
Yeah.
perfect.
If it gets obnoxious, we'll have to do the hand raising thing.
Okay, perfect. Yes, yes. So yeah, please interrupt me if something's unclear. If you have a question, I'm happy to answer. So okay, introduction on gravitational waves, a bit very short. And then I will introduce a toy model because originally we thought, well, if we want to answer this question, we don't have too many microstate geometries available for which you can actually solve the scalar wave equation. That has recently been solved, by the way, and Pierre will talk about it. Pierre Heidemann will talk about it tomorrow. So we started doing this in a toy model. That's the second part I will talk about. And then we with the paper have three main messages, three fun applications of this toy model, and that's what I will end with. So let me start first with the introduction. Yes, and I'm gonna drop this. Okay, so gravitational waves, and in particular gravitational wave echoes. There we go. Yes, here we go. So I'm just gonna focus on a massless scalar field for now. I can write the wave equation on a particular background. In terms of a tortoise coordinate x, I stole this figure from a paper by Cardoso because it's a very nice one. So here it's r star, the tortoise coordinate. I'm going to call it x to be in line with the rest of the talk, and also some other instances in literature and our paper, etc. So if you send in a wave packet from infinity, it will be reflected, will be scattered of this potential barrier for the black hole. So this is in the tortoise coordinate. Positive infinity is asymptotic, the asymptotic flat region. The horizon is at negative infinity in these coordinates. So you scatter a wave off and you get a signal. This is basically the ring down signal that you would also observe in a gravitational wave type experiment. And you're just modeling it now with a scalar wave packet. Now, if you replace the black hole by something else, say a wormhole, something that has inner structure, another copy of this bump, or some artificial reflective surface that you can invent, or some other model. There is plenty of models that is going around that are being studied in four-dimensional physics, things like gravastars or boson stars. I mean, there are many things you can try, you can invent, you can do, but it's always the same main physical thing that's going to happen is that the wave, as it travels down, is going to get reflected another time, it's going to get out again. That's an echo. Part of this wave is then going to go in again, get out again, etc. This continues again, this multitude of echoes. So this is the basic physical picture. This has been discussed for many years. Actually, it became popular after 2016 when Cardoso and collaborators showed this in a paper explicitly how it goes. But actually, it was known for a longer time already. Even in the context of microstate geometries and the fuzzball proposal, I'm listing it here. Also there for these kind of geometries, as long as you have a potential that has this inner boundary condition that can reflect, meaning in the case of a microstate geometry, for instance, it means that the potential will go up. You will have this kind of effect. So it's very universal, it's robust, and it's been identified as a prime signal in gravitational wave literature to just look for exotic compact objects, an object that is more compact than a neutron star, but not a black hole. And at the classical level, this is a good observable to look at. And also recently, there's been quite some activity in doing this for microstate geometries, calculating quasi-normal modes, and from this a time signal, and you can get similar types of behavior. So this we know. Now, the big question is, of course, this holds at the classical level, but this is really what we expect for microstructure, for the microstate of a black hole. The typical black hole microstate is
Bert, can I ask?
Yes, please do.
Can you go to the previous slide?
Yes.
Can you explain to us the difference between the three different plots, empty shell, gravastar?
Yes. So the universal. Well, let me first go back here. So what gives you, I didn't put it on this slide, it will come later, but let me also explain to you now in words, and then formulas will come later. But what you have is that this echo is a modulated copy of the initial ring down. The modulation is set by a reflectivity that depends on the frequency. And the reflectivity depends on the particular boundary conditions that you put. And in this case, the boundary conditions, they are fixed by the potential. And since the potentials are different, the reflectivity is going to be different, which means that the echoes are going to be a bit different. The amplitude might differ, and the particular time scale between echoes will also differ. This particular time scale itself, it depends on the distance or the travel time you need to go down the throat, be reflected, and back. And because of the particular solution that are taken, this is a wormhole. This is an empty shell, meaning that it's just a shell that's put there that's matched with Israel junction conditions that reflects all of the radiation. This is a grava star that's similar to a shell, but it's a particular construction with a de Sitter interior. And based on the particularities of these solutions, meaning that the location of these reflecting boundary conditions, you get a bit of a difference in the time scales.
Can I just follow up? So suppose you get an actual signal. Maybe you're going to discuss it later, but if we do back of the envelope, how distinguishable are the three cases?
Oh, yes. Yeah. Well, at the moment, in current gravitational wave observations, it's very hard to distinguish. At best, one could hope to just see the signal, and given the signal-to-noise ratio that we have now, seeing a particular one particular echo is even very hard to do. But what you can do is stack up the amplitudes, basically, because it goes on for a very long time. There's a slow decay. Discerning between different echo signals, I'm calling it echo for exotic compact objects, so echoes from ECOs, echoes. Seeing the difference, I think this is more something for the future, but this can indeed be done. But for that, I will mention something later. You need a bit to know some details on at least phenomenological details, like how do you parameterize the reflectivity, and can you reconstruct the potential from the echoes? There is some work on this by Kokotas and his former PhD student and other people. So around 2017-18, this has been studied. So if you wish, I can point you to the papers.
Surely, at the very least, from the delay between the echoes, you can deduce something about the separation of the lumps and the potential.
Yes. I will come back to this later. I chose not to give the formulas here, but do them when I compare them to microstates. So I will. Yes, you're absolutely right. So this time scale between the ring down itself and the first echo, it is proportional to the amount of redshift to the square root of GTT, basically. So the redshift at the location of this reflective surface or a reflective boundary condition. And this is also something that you see in a microstate geometry, but I will come back to this in detail later. Any more questions on these echoes? Okay. Yes, then I will continue. So they are a classical observable in the sense that they are universal. You can even prove in 4 dimensions. This is work by Herdero that I didn't cite, but when you have something that's stationary, so that's cylindrical symmetry, basically, then you can prove that whenever you have a horizonless object, that it must have a potential that goes up and has this reflection. So it's a pretty universal thing at a classical level. For a quantum, a typical black hole microstate, you actually expect from just the huge amount of exponential in entropy amount of states by Boltzmann's law that the variance around the mean, the typical mean and observable is the black hole expectation value, that the variance will be suppressed by the entropy or an exponential of minus entropy divided by 2. So then how do you reconcile this with something like an echo, which is of course at the classical level, right? So this is a question that we're interested in and that we want to try to see if we can answer this a bit in a toy model. And second, even at the classical level, there are particular microstate geometries now, superstrata, very peculiar ones with, at least in the near horizon decoupling region, a separable wave equation. For those, you seem to have these echo signals, but a more typical coherent state that might also be a geometry might not have a separable wave equation. It might not have a single throat from which you can bounce off. So even there, for these classical solutions that are more complicated and might be discovered in the future, even there the echo signal might disappear altogether. So we just wanted to understand, with this in mind, what can we do with these echoes in a bit of a microstate setup, and how can we play with them? Okay. So what we'll do in the talk, so what we did in the paper, is to take this to the setup where these black hole microstates and their geometries are best understood. That it's the context of the 3-charge black hole, supersymmetric black hole, or a microstate. And we will send in scalar wave packets, as has been done in the past, also in particular microstates. But we will not choose to go for a particular microstate, but for a toy model. You have the asymptotically flat region, develops a throat. There is an ADS3 times S3 region. Actually, it's the BTZ black hole in ADS3. And we will put in a wormhole. So why on earth, you might ask, do we want to study a toy model that's a wormhole to say something about microstates? Well, at the time when we started this project, there were no microstate geometries available that were asymptotically flat and in which you could solve the wave equation and such that the throat itself becomes very, very deep so that you have truly an echo signal like what you see in flat space. This has been solved now recently in a paper that Pierre will talk about tomorrow. But even then, it remains interesting to look at these toy models because you have one controllable parameter that they depend on. So this means with this one parameter, you can just capture many details in one parameter that you can control. And then I come to the 3 main messages that I want to give. And one is that a toy model as a wormhole can actually capture features of the microstate structure in terms of this parameter lambda in a manner that I will make precise in the second half or the third part of the talk. Second, we will use this to relate holography, basically a 2-point correlator, to some of the 4D gravitational wave language. So this is related to Costas' question and what Nick was asking. So in 4 dimensions, what sets the parameters of these gravitational wave echoes? It's a reflectivity. You can think of how close the structure is to the horizon. We will try to see what that becomes for a microstate. Sorry, I'm clicking. We will try to see what that becomes for a microstate, these parameters, by going through the toy model. And last, because the toy model is so simple, depends on one parameter, we can actually perform an ensemble and see how the echoes are suppressed if you take an ensemble instead of a particular geometry. So these are the 3 main things that I want to do. Are there any questions at this point? Okay, then I continue while keeping track of time. So this was the introduction, our 3 messages. Now I want to discuss the toy model, the wormhole itself, the wave equation that we do in it, and then at the end I will come back to the messages. So what is our setup? We studied the massless wave equation in a 6-dimensional background of the 1D5P black hole. Looks like this. But for the 3 coordinates t, y, and rho, down the throat becomes an ADS3 region. When it's a black hole, this is the BTZ black hole. For our microstate toy model, we're going to replace the BTZ black hole by a particular wormhole that I will discuss on the next slide. And what we will calculate is we want to get a bit of an idea of the time signal. So we will start with the quasi-normal modes. At the end of the talk, I will also talk about the signal in the time domain. And we will do this both in 3D, in this wormhole itself, in 3 dimensions, in the ADS3 region, and in the asymptotically flat 6-dimensional case, which is related also to the recent work on superstrata, and related to, and see what kind of general messages we can get from this at the end. Okay, so this is the setup. Replace the BTZ with a toy model, calculate quasi-normal modes in 3 dimensions, in 6 dimensions, before we go to the interpretation part. The wormhole is inspired by a wormhole introduced in 2004 by Solodukin. That's on the left-hand side. This was extremal. Sorry, what am I writing? This should be non-extremal and rotating. It's the other way around. Sorry for that. So Solodukin introduced a non-extremal rotating. Sorry, what am I saying? I need to say it wrong. No, it's non-extremal and non-rotating. Okay, I'm getting confused on my own slides. So Solodukin constructed a non-extremal wormhole that has the same behavior as the non-rotating BTZ black hole. How do you do this? You start from a 3-dimensional metric, depending on certain functions. It can describe the BTZ metric, for instance. But what we want is to change the metric at a particular location that is proportional to the horizon coordinate of BTZ, plus a correction determined by a parameter lambda, which will determine how deep the wormhole throat is. And for lambda equals to 0, this is just the BTZ metric. So what Solodukin did was do this for non-extremal, non-rotating in this particular way. You change one of the functions with respect to BTZ, the other one is the same. In our case, we make a version inspired by this that is rotating extremal because, of course, the 1D5P black hole that we study, supersymmetric, is rotating extremal. So this is what we need. And therefore, you need to change both of the functions in a particular way. What is most important, I will not go into detail in terms of the wormhole structure and geometry. I want to skip to the 3 messages as soon as possible. But the thing to remember, because this is a parameter that will come back a lot, is what we could call the length of the wormhole, or some optical length, how deep it is, how long the throat is related to the redshift. I define it as the travel time from the ADS boundary to the wormhole throat position, r lambda. When the wormhole, yes, a question.
Is this still a solution to the equation of motion of the same theory that you started?
Yes. So there I'm cheating a bit, of course, because I need to add some, well, exotic matter that does not agree with the regular energy conditions. But I'm putting that aside for now, because what I want is to study the geometric properties instead of really looking into the particular source that I'm putting down the bulk. But in terms of physics, physical intuition, this solution does just become the BTZ metric asymptotically. So asymptotically, it is philosophically like a microstate in the sense that you have the same fall, etc. And that's what we're interested in, is gravitational interpretation at the moment. Okay.
Okay, thank you.
So and yes, and to complete this, if we really want to discuss an actual state in the 1D5 CFT, then of course we should go to the microstate geometries, etc., for which there are less available at the moment. So this length of the wormhole is the travel time from the AS boundary to the wormhole throat. When it's non-extremal, this is logarithmic in the parameter lambda. When it's extremal, it's a polynomial. It's 1 over lambda squared, basically. Keep this in mind, because I will mostly be doing extremal, but when it goes to interpretation, I will jump to this setup. And this logarithmic behavior is important because that will lead to certain changes in terms of length scales, etc., that I will talk about later. So this is important to remember. The length of the wormhole, I will speak a lot about, this L subscript lambda, which is just a travel time from the AS boundary to the wormhole front. Another reason why we took this wormhole is because historically, a 4-dimensional version of this in flat space by Solodukin and Damour, actually there it was the first very active propaganda to study gravitational wave echoes from such wormholes. So therefore it's also natural to look at the AS3 version of this. Okay, so I will do 2 things, 2 analyses. Analysis 1 is do the scalar wave equation in 3D. Analysis 2 is do it in 6 dimensions and then relate it to 3 dimensions. I will not give too many details because this is in some sense standard stuff that has been discussed for other solutions. I will just review it so that you know what we have done without going too much into the details. So we do the scalar wave equation. We take a massive scalar because we will see if it comes from 6 dimensions, and we really want to be in 6 dimensions where the black hole lives. If you reduce to 3D, you can develop a mass that's related to angular momentum on the S3. So we keep a mass here. You separate the wave equation in a standard way. The only thing that I do extra is introduce an extra function h here, because there is some redundancy in how you choose your wave equation, and we want to make the redundancy such that you have a Schrödinger form which is easy to solve. It's standard. You get some intuition, and we can apply a method that has recently been developed on my next slide. The potential tip looks like this. The BTZ black hole is this dashed line. That's the potential for the BTZ black hole, actually moved a bit to the right. The wormhole potential is almost identical all the way down the throat, where it meets another copy, an inverted copy of this BTZ type metric. So it's a really simplified version of the potential that you can imagine for a microstate geometry in ADS or something else. And the nice thing about the Schrödinger form is that you can actually then easily put a WKB method to work. And what we want is to find the quasi-normal modes, in this potential. Now, the quasi-normal modes in this geometry, they are in the standard ADS-CFT language related to the poles of a retarded two-point function in the frequency domain. So if you write down this retarded two-point function where O is the operator dual to the field phi on the boundary, you could go to the frequency domain, let's call it the response function R, and it's this that gives you the poles, or the poles of this function give you the quasi-normal modes. I'm using notation here that I think that Pierre might be using, so I thought, why not use the same notation throughout the conference? Let me just do my best in starting this way. So source on the bound is given by beta, alpha related to the VEV. You take the ratio, this gives you the response function. And now you want to calculate this function and get its poles. Now, it's very important to know that while the first one you can actually get the non-normalizable mode, you can get from just making the expansion near the boundary. The second one, the VEV, you cannot. You really need to have information on what happens inside this potential, inside the geometry. You need inner boundary conditions. And for that, Josif, Nick, Ruben Monten, Pierre Hedman developed a hybrid WKB method where you match two different solutions, an asymptotic solution where you just write down the solution in the BTZ metric, the exact potential here, and then a WKB method here in the bucket where you can easily apply WKB methods. You match the two and you find the response function. Now, the response function, if you do this, it's related in a particular way to the response function in the BTZ black hole. It's given by the real part, the imaginary part, with an angle, I could call it an angle theta here, that's related to the integral of the potential between the two turning points. For our wormhole, we just apply the method. So we take the method, we apply, we calculate. Between brackets, the method is actually a bit overkill in this case because for the leading order, there are other ways of finding it, but it's a nice application of the method. The normal modes, they're not quasi-normal, they're normal because you're in between the boundaries, so you just get normal modes, are given by the poles of the function theta. You can calculate that theta is proportional to this travel time, this throat length that I introduced. And if you then work out the quasi-normal modes to have poles here in the tangent, they are given like this. So you have an integer m. K was related, let me show you. K was related to the separation of the wave function. L has to do with angular momentum on the S3. And the important part to notice is that the difference between two consecutive quasi-normal modes, so the spacing, is just the inverse of the travel time down the throat. Okay, there are additional corrections that I'm not giving here that you can calculate this way. I'm just not specifying them. I just want to focus on the beating behavior. This is all as expected because this spacing is proportional to the inverse of the travel time, and we know what this is. No surprises here. This is what you do if you do it in 3 dimensions. The second thing that you could do, and that we did, is how to connect this to asymptotically flat space. Therefore, you use a matched asymptotic expansion. You write a 6-dimensional metric again. You separate the wave equation here in 6 dimensions. Now it's radial coordinate r. I'm calling it g of rho here. Radial coordinate rho, I'm sorry. G of rho, not phi anymore, because it's a different function. You solve in the asymptotically flat region, in the BTZ3 region. You match across the neck. This is standard, has been done also for particular solutions in the D1, D5 system. And you can then get the quasi-normal modes from this by doing this matching, by demanding that the two expressions that you find for the function g are equal in the 2 regions across the neck. For small values of the decoupling parameter, and my apologies here, it should be ry squared. That's the radius of the y circle in your geometry. Alpha prime is string length squared. For small values of this decoupling parameter, the quasi-normal modes will fall apart as a real mode that you get from the BTZ3 region only. That's what we had on the previous slide, plus a small correction. This has also been observed, by the way, this type of reasoning in terms of microstate geometry separately, but I trust that you will hear more about this tomorrow. Let me focus now on the result for the wormhole. So the first part is given solely by what happens in 3 dimensions. It's real. The imaginary part comes from the correction. So if you write down the correction, it contains charge of the background, it contains ADS length, etc., various parameters, and you see the real part of the frequency. There should be a tilde here, I guess, to be consistent notation. The real part of the frequency, you see it appearing. I'm not asking you now to go over the entire structure. The most important thing is that in the large frequency limit, at least, the imaginary part here of this correction scales as omega to 2L plus 3 with L, the angle given related to the angular momentum on the S3. And the lesson here, which is also confirmed in actual microstate geometries, is that the time scale related to the real part of the frequency comes from the throat region, while the decay time related to this correction comes from the coupling to flat space. These are the calculations that I wanted to give. Okay, now I want to come, because I found this the most important part, to what can we do with such a toy model. 3 messages. The 3 messages are as follows. First, toy models capture features of microstate geometries. There are many things that toy models do not capture. This wormhole, for instance, cannot capture a feature of microstate geometries. The fact that you have ergo surfaces or evanescent ergo surfaces where the redshift vanishes. This just doesn't happen. But the fact that you have a throat that ends in a structure is similar, and this we can connect to particulations of microstates. This we can then use our wormhole to link to flat space gravitational wave phenomenology. That will be the second one. And then I will end with an ensemble over the parameter lambda. Okay, so 1. Physics of microstates. Well, let me first go back to 4 dimensions. Already in 4 dimensions, and this goes back also to a question that Kostas was asking in the beginning. The typical quasi-normal modes of such potentials fall apart in a real and imaginary part. The real part determines the timescale, the travel timescale that you have to go up and down this throat, get reflected and come back. The imaginary part determines the decay timescale of the echo. And there is a universal scaling in this decay timescale that has been discussed before, that the decay timescale is related to some tunneling amplitude, or the inverse of a tunneling amplitude, and the decay of the echo amplitude itself over consecutive echoes. And if you put those 2 together, you can already qualitatively see that this has this particular scaling with the real part, which is, by the way, also confirmed in higher dimensions in terms of microstate geometries or these wormholes, etc. So this is just in general. What do we observe? Same type of behavior. The travel time scale is proportional to the length of the throat, inversely proportional to the real part of the spacing in frequencies. The decay time scale comes from the coupling to flat space, is related to the travel time down the throat up to this particular power. And this is the same as what would happen in a microstate geometry if you just take a distance and only ask about these time scales. They are similar. They have been discussed recently. I refer again to Pierre's talk for this. And this just suggests that if you want to use a wormhole like this to capture very roughly, to play around with it and to pretend that this acts as a black hole microstate, you just identify this length with a typical energy down the gap, which is a natural thing to do. What do I mean by E gap here? That is the mass gap. It's the energy of the lowest excitation down the throat on top of this microstate, this supersymmetric microstates. Okay, so this is just identifying one with the other. Now, what can we really do with this? Now I want to come to the flat space window, let's say. I want to connect a bit to what has been discussed in terms of 4-dimensional gravitational wave echoes. And there are 2 things that I want to talk about. So this is slide. This has a bit of the details of what you see and how to get echoes from these kind of potentials. So there are two things you can do, and I want you now to just focus on the figure for a moment. So forget about the text, just focus on the figures. There are two things that you can do. Either you can just look at different potentials, scatter waves of them, see what they are, and maybe try in an experiment to see whether you can reconstruct these kind of potentials. You can also effectively try to capture the details of the potential, and now it's time to go to the text. You can try to effectively capture the details of the potential in terms of some parameters, some effective descriptions. I call it echo phenomenology. And two of these parameters that I mentioned in the beginning also are some reflectivity that you could define, and an idea of how close you are to the horizon. Now, this reflectivity, where does it come from? You put at a position, this is for a Schwarzschild black hole, you would put at r equal to 2m Schwarzschild radius, plus a small correction divided by a dimensionless number, epsilon. You just say, well, what if we replace this potential by just a black hole potential with some reflective boundary conditions? Then near the horizon, you replace the boundary conditions for the black hole by something that also reflects, also has waves coming back out. The reflectivity will be frequency dependent. The particular way which is frequency dependent is determined by which type of potential you want to describe with this effective description. So there is some reflectivity, and how close you are to the black hole is determined by its closeness parameter. For instance, if you want to have some structure, a wormhole throat, where the throat, the connecting part of the throat is really a Planck distance away from a horizon, if you want to interpret it like that, then you need to choose epsilon to be very small. If it's Planck distance, I think it's 10 to the minus 40 or something like that. And certain parameters in your gravitational wave echo signal are determined by this reflectivity and how close the structure would be to the horizon. For instance, the echo timescale is dependent, it depends logarithmically on this distance. So this is just a redshift here that you see. The asymptotic wave that you receive as an observer is equal to the one for the black hole, plus an extra contribution, which is the part of the wave that you have from scattering, from being near the horizon of the black hole, but it's modulated by this reflectivity in a particular way. If there's no reflectivity, it's zero. You just reproduce the black hole result. If there is a reflectivity, then you get something like this. And the poles of this function, the poles of this ratio, give you the quasi-normal modes. So when the denominator is zero, this is what gives you the quasi-normal modes. There are more phenomenological parameters that people have defined to talk about echo structures. For instance, a gravitational wave echo is not always equidistant. It's different when there is rotation, etc. I refer for that to some reviews because I just want to focus on these two, reflectivity and how close you are to the horizon. Okay, so how do we do that for our wormhole and interpret something for microstates? Let me start with the reflectivity. Okay, so let's do the same as what we did for flat space. So we just pretend that we are doing the black hole potential, but with reflective boundary conditions. In flat space, this is what you get for the wave equation, but you can also do this in ADS3, and you can reinterpret your holographic response function in terms of such reflectivity. You just write your response function as though it comes from a potential that's all the way identical to the black hole potential, but has some different reflective boundary conditions. And then there is a fixed relation between the reflectivity and this function theta that was introduced earlier, which is related to the potential. So in this sense, you see that this effective reflectivity that is discussed actually immediately probes the geometry of the microstate in a particular way. And it's also related to its holographic response function in this way. Note that the quasi-normal modes in flat space are determined by these zeros, the zeros of this function, while for this response function and the ADS3 geometry, the asymptotic to BTC3, the zeros are determined by 1 minus, or it's a bit different. And this also explains the difference that you get in the quasi-normal modes and the absence of the imaginary part. Okay, any questions? Geoffrey, I see you. Do you have a question?
Oh, sorry.
No, okay. No,
No, not for the moment.
no, I just saw your name popping up, so I was confused. Okay, so this is just expressing this reflection coefficient in terms of some details of the microstate and relating it to the response function. The other thing that you can do is to just, for fun, see, well, at what distance from a would-be horizon is this microstructure? So for 4D, in 4 dimensions, these reflective boundary conditions, if you insist on just taking black hole potential and modeling it as just some particular reflective boundary conditions, then it comes from a certain distance from the horizon. If it's Schwarzschild, it's very simple, it's something like this. Now this parameter epsilon, there are many different ways of going about with it. You don't really have to imagine structure there. You could even equally well either relate it to the proper distance from the horizon. You could relate it to the actual value of the redshift at this position, which is logarithmic in epsilon, or you can relate it, as we have been doing, to the travel time down the throat up to this position, which is also logarithmic. Now, if you want to do this for a microstate geometry and want to interpret kind of, well, how far from the horizon would this be? You don't have all these options available. For instance, for extremal black hole, proper distance to the horizon is infinite anyway, so this doesn't really make sense, but you can still try to at least get a coordinate distance. And how we will do that is to just compare the travel time in a microstate, or better yet, in our wormhole solution, to the corresponding travel time that you would have in a BTZ black hole. And this gives you an idea of how far you are from the horizon. Just a fun thing to do. If you compare these travel times, this is for the BTZ metric. It's related to the coordinate where you put your reflective boundary conditions and the horizon to a particular power. In the wormhole metric, it's related to the this throat length that I introduced, the travel time, which is related to the wormhole parameter. I'm sorry. And this you could compare to an extremal microstate where you know that the travel time is related to the gap, the mass gap. If you do this, then you would say that at least in coordinate distance, the object only differs from the black hole at scales that are inversely proportional to the entropy, which is not heavily suppressed. But there's a but. We're interested ultimately in extremal non-extremal microstates. Sorry. So when you imagine a black hole that's near extremality, then because of the nature of microstates, what you expect is actually that this travel time will not differ too much, but the travel time in the corresponding black hole will become logarithmic. Once it's near extremal, it's logarithmic, and it's no longer related by a rational function. It's going to be logarithmic.
I have a question. How did you get the NP into the R0 minus RH?
Oh, yes. Okay, I didn't give the details. So how does the NP go in? So E gap is actually measured. It's dimension full, and it's measured in units here. Sorry, I'm going back. What you're missing is the radius of the Y circle, right? So this goes into the calculation. And when you do the proper calculation of this, the time scale in BTZ, you're gonna also, you see that there's a mismatch in dimensions. Here you have the ADS length appearing, which is related to QP. All right.
The ADS length for the D1D5P system, it's not.
Sorry,
sorry. Related to Q and Q5, but there's an ADS2.
Sorry. Let me see if I can get it straight. Where's the way? Sorry. Yes, I'm saying it wrong. Excuse me. Let me go back. What's missing here is not the ADS length. I'm sorry. What's missing here to measure dimensions is a factor of the horizon area, the horizon radius. The horizon radius, and the horizon radius is related to QP.
Mm-hmm. Okay.
So yes, I decided I changed the slide yesterday, but I decided not to give the details. But you're right, the details become interesting. So let me just repeat so that we're all on the same page. When you calculate this travel time in the BTZ metric, it's actually it's proportional to the distance from the horizon, but the proportionality constant depends on ADS length and the horizon radius, which contains the number of momentum modes. And
the horizon size on the y direction. It's the y. It's the size of the common
yes,
geometry.
yes, but all these numbers, so ADS length and horizon radius, they enter in the timescale in BTZ, and the radial, the length of the y circle enters in this timescale in the gap. If you put all of that in and you run the numbers, then you see that it becomes the entropy.
Oh, nice.
Yes.
Okay, I've never seen
So
that calculation, so I'm quite.
Yeah, well, I decided yesterday to take it out because I thought, well, it's actually, if you look at it, it looks trivial because it's just numerology, but it's fun to see. It's fun to see this happening. And so this is number one. So for an extremal microstate, the distance from the horizon is 1 over the entropy. If you look at something that's near extremal, you expect the timescale to be the same, but the timescale in BTZ becomes logarithmic. So what's going to happen here is that this, instead of 1 over the entropy, you're going to get exponential minus the entropy. And since this is suggestive that for a non-extremal microstate, that even though the geometry can be smooth and perfect and all that, if you insist on interpreting it as small corrections to a black hole, then it's really exponentially suppressed corrections to the black hole, which doesn't really seem to make too much sense from the black hole point of view, but geometrically it's perfectly fine because for a microstate it works. The only jump that I made was to assume that also for a near extremal microstate, the timescale is going to be similar to what you have in the supersymmetric microstate. Okay. Yes. So this is this distance exponentially suppressed. And then after this, there is a third.
Excuse me, may I ask a question at this point?
Sure, sure, sure.
Isn't in fact this result perfectly consistent, since in the classical limit where the black hole entropy is infinite, this should be 0, and therefore R0 cannot be distinguished from our horizon.
Yes, yeah, you're absolutely right. But the big question is it going to be suppressed with a power law, or is it going to be suppressed in an exponential fashion?
Oh, yeah.
And this is important because if it's power law, it looks like a perturbative correction from the black hole point of view. If it's exponential, it's more like a non-perturbative correction. And then this would also be in line with known discussions, as I said, thinking about the variance of around the black hole, the mean in a black hole background, that this is exponentially suppressed. It's all just perfectly consistent, and you can still have these microstate geometries, even though
even though these microstate geometries are in fact a quantum effect, they do appear in classical issues. That's the message that to take.
Yes, exactly. So this exponential suppression really points to a quantum effect, and still they are classical objects.
And I just want to say, we left a lot of time in between seminars, so do not worry about overrunning slightly in the time. We want to encourage discussion. So
okay. Well, thank you. Well, actually, I assumed, knowing the style of Saclay seminars, that discussion would happen. So I took this into account in not speaking a full hour. So we might land there anyway. So let's see. Okay, so this is being exponentially suppressed. Now, let's see what happens if we take an ensemble, a microcanonical ensemble. Let's play a bit around, but do this in the wormhole setup. So instead of doing this with the microstate geometries, for which it might be a bit hard to do, let's just take our wormhole as an excuse to set up a toy model microcanonical ensemble. So this goes in several steps. So let's go to the first line. We calculate this. You can calculate. You can get the response in the time domain or in position space in an individual wormhole state. So in a geometry, this would be, you can imagine a 2-point function in a state dual to this geometry, labeled by the parameter lambda. There's a first response, and then you have this collection of echoes. You can also calculate it. We did this from summing up the quasi-null modes again. You get this rough behavior, And now the question is, what happens if you take an ensemble? So you take a state that is built up out of several randomly selected among the possible wormhole states, all with different throat lengths. So it's a very, very crude model of an ensemble of microstates, but just let's see what happens. And we want to again do this two-point function in the background of this heavy state of the ensemble. Now, we're not going to do this with this full correlator, but just simplify the correlator to have its main features. It has just some decay, which I drew by hand, so it's a very bad drawing, but this represents the decay as you would have in a black hole system. And then the echoes we just represent as block functions with a certain width, 2 delta, and the distance between the echoes is this L lambda parameter for every wormhole separately. If you do this calculation, you do this ensemble, you work it out, you find that this is identical to the response for the black hole plus a correction. And the correction is proportional to the area under a curve of one particular echo, h times delta, divided by the length, the travel time in the wormhole, the maximal possible travel time in your total ensemble, which you can work out to be related if it's non-extremal, because then it's most drastic in a sense. If it's non-extremal, it's related in the following way to the wormhole parameter. I didn't see immediately an exponential suppression here, but there is a strong suppression of the echoes if you take this ensemble. So this was just another fun thing to do, to just play around with these wormholes and see what kind of ensembles that you get. If you take an ensemble like this, and you see that the echoes are suppressed, you can also wonder about when, in terms of unitarity, when do you see a recurrence, a Poincaré recurrence, so that this two-point function becomes identical to what you have in the beginning.
Can I ask one question about the previous slide?
Yes.
So what are the factors B sub L?
Oh, yes. They correspond to just a randomly selected, well, let's say take a Haar measure, select numbers over the possible allowed values of lambda. And for that, we parameterize this in terms of the different throat lengths that you can take.
And why do you call this microcanonical?
Oh, did I miss it? Yes.
I don't know whether you were. I'm just asking. I don't know whether in what sense.
Well, I wanna fix all the wormholes that have a particular value. So I take well, just as for microcanonical, typically you would fix an energy, right?
Mm-hmm.
So here, I want to fix a particular a parameter and then see how many I have around that parameter.
Are you doing some kind of Gaussian normalization around some chosen average value? Is that what you're pegging, the average value of lambda in your distribution?
Yes. Well, we did several calculations, and then that was one of them to see how it works out. But the result is always roughly going to be the same.
Okay, thank you.
You're welcome. Yes, and then last but not least about this recurrences, say that you start stacking up and you take different wormholes, different lengths that you can have between the consecutive echoes. You can also show that there's going to be this type of recurrence. Note that it already happens at the classical level in the non-extremal wormhole introduced by Solodukin, because echoes are not perfectly equidistant. There is a small correction, and this small correction leads to a classical recurrence time. But also statistically, you can get this, and it's a double exponential by tweaking, by writing the typical distance between two consecutive echoes as a number times the width of each echo. You get a very large but calculable time before you just randomly get the same signal again.
So what is that log acting on? Is it acting on the
Oh, it's only n, only on the n.
That looks better then.
Yes. Yeah, the brackets are imaginary. Okay, so yes. So this already brings me to my last slide. See, I was really aiming to be on time. So in terms of conclusions, I presented a toy model for black hole microstates, a rotating wormhole inspired by Soloduki's work of more than 15 years ago. And I try to give some interpretations. One is that with this toy model, you can try to look for the location of the microstate cap, the microstructure, and you see that if at least for new extremal solutions, it's suggested that it's exponentially close to the horizon. After averaging over an ensemble in a particular way, you see that the amplitude of the echoes is indeed decreased as you expect. I would, by the way, it would be interesting to see if you can do some kind of ensemble over a particular superstrata or something to see how this happens. And I also discussed these Poincare recurrences. And then just to advertise as an upcoming application, we went a bit crazy with our wormholes. And you can also use them as a test bed for calculating this two-point correlator in using real-time ADS-CFT methods. So instead of having a black hole, you have a well-defined geometry that doesn't have ingoing boundary condition at the horizon, but something else. And you can actually unleash these methods just as a test case to see what it happens compared to the WKB or hybrid WKB methods of Josif and Nick and Pierre and Ruben. And this is also in an upcoming paper. Okay, well, that was it already. Thank you very much.
Well, thank you. Do we applaud, I guess? Reactions, yes. There's a button. So, questions, people? It's one of Josef's roosters.
I have a question.
Yes, go ahead.
Hi, Bert. Very nice talk. So my question is about the reflectivity coefficient you had in some of the models towards the second half. So one might imagine, yeah. So here, if you had some particular microstate geometry, you have a certain reflectivity. If you have a more typical black hole microstate, you might expect some more stringy physics, which would lead to more absorptive properties, and that this reflectivity might depend on the microstate in such a way that for very typical microstates, it might be quite small. And my question is really about the present and future detectors. Is there any sort of back of the envelope expectation of how small this could be, but still be detectable? Or another way, how big does R have to be for it to be detectable in the near future?
Well, in the very near future, so I'm thinking a bit. I think there was a paper recently. I'm gonna send you the reference, but I have to look it up. So in the very near future, it really needs to be close to 1 basically, or -1 depending on our conventions. But so there should be almost total reflection to be detectable at the moment, because the signal to noise ratio of current detectors and the frequency band, it's already very hard to find the ring down, let alone this very late stages. But if you're thinking about 3G detectors, Einstein telescope, for instance, or Cosmic Explorer, something like this in 2030s, then you could go down a lot. And the fun thing is that actually, based on this reflectivity, there are other observables that also become interesting. So the fact that you would have some effective reflection not only leads to echoes, but it also leads to effects in the inspiral of the gravitational wave. You can get tidal effects that play a role during the inspiral. You can get a sudden absorption, so due to a resonance that's triggered, which is basically the same type of mode that you get in these echoes. So there's a lot of extra things that can go on. And then the thing that I was wondering, so but because it's a very interesting question that you're asking, is what kind of effective reflectivity that you would put out there that has this absorption of a more typical microstate, because you might imagine that it's still frequency dependent, that for certain frequencies, like in your fuzzball complementarity idea, for certain frequencies it's completely absorbing, for others it might be reflecting, and depending on where this change happens between reflection and absorption in frequency space, you will either see nothing or a very strong signal, and this is something that in principle is detectable. Right.
Yeah, indeed, it could be frequency dependent and microstate dependent. And I think the interesting question would be, if you go to very typical microstates and the frequencies which are the most reflective, how big is curly R? I mean, if you still have it only down in the % or less level, I guess that would probably wipe out any signal in the near future. But if it might be larger, then that's where you get all this interesting physics that you've been exploring.
Yes, 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 absolutely, absolutely.
I suspect that it's going to have to be something which is highly, highly suppressed from a typical microstate. It requires a very high degree of coherence, I think, to produce an echo. And so it's sort of a bit like pointing a radar gun at an aeroplane and you go, okay, I'm going to measure the aeroplane, but there's a whole pile of gas around the aeroplane. Can I expect to see the coherent states of the gas? And the answer is no, it's just too random. But on the other side of the coin, though, the viscous drag created by all that stuff around the aeroplane is very, very significant. And so therefore, the very low energy excitations I would expect to be seen in spiral rather than so much from echoes. I don't know whether you think that's right or wrong, but go for it.
Well, you expect to see it during in spiral. Well, the typical frequencies that are accessible in spiral, they are also dependent. I mean, they are also the ones that would show up in these echoes, right? So I'm not 100% sure. I think if you want to see something like a quantum effect, then I think even the merger, if you're really wishful thinking, might be better, because that's where you get the most violent effects and where you could hope to find something that's less typical. Okay, I think it's good to think about. Yeah. Well, as a side note, you were wondering about very low excitations during the in spiral. In the in spiral, it's also a lot harder to measure. If you're thinking about resonant effects, for instance, this is something that is very hard to measure from this kind of objects, because you want to measure a phase shift. The phase shift that is builds up slowly is not too large, so it takes some time. But there are other effects of tidal forces and tidal heating that might play a role.
Can I ask a question? You mentioned obviously that when you have this wormhole, in order to actually have it, you need exotic matter.
Yes.
So how sensitive, and of course, so the question is, this wormhole, if you don't, or if you're not careful, will have in fact a finite lifetime itself.
Mm-hmm.
How sensitive is this calculation to the effects of the finite lifetime of the wormhole?
Well, this is something that we have not looked at, so I don't know. I don't know what the time scale of that lifetime would be actually. So it's hard to compare out of hand. No, I don't know the immediate answer. We took these wormholes as a toy model, as an excuse. Let's say like poor people's microstate geometry, but they just serve their purpose in having an actual doable geometry that you can test from. But I don't know about the decay time scale of the wormhole.
So it's not necessary to worry about this thing. You can just take the final result. We have this wormhole. These are its effects. The effects of the wormhole are just encapsulated in this reflection coefficient.
Yes. So it was just a tool to go to this effective description, to be able to, and meaning this reflection coefficient, meaning the distance to the horizon, meaning also what I said about making an ensemble, just something that's controllable, has one parameter that you can play with, and it serves its purpose.
Any more questions? I have another one. I was struck by this calculation you did where you showed this transition from 1/s black hole to e to the minus s black hole in the time, the travel time. I mean, it strikes me that should have some huge holographic consequence that when you go from extremal to non-extremal, but I can't quite put my finger on something sensible to say.
We have some slides with those notes. I mean, in principle, we have, I mean, you know, if you have the slides which contain the calculation, I mean, you're like, you know, some more details on that.
I guess I'd like to say more about the physics of what that really entails. I mean, that's something I've never seen before, and it's
Well,
cool.
I put in a lot of stuff here that I deleted yesterday. I don't know if I can pull it out, but this will do it. So yes, here it is. So yeah, this is even a different notation, but this is the relation that you get if you pull this calculation through. Is that the distance here? I call it delta S, but it's similar.
So this is the distance in the proper frame of the in the proper time in the proper frame of an infalling observer, right?
I thought it was the time measured in infinity because it's an energy gap.
The time measured at infinity. So delta t is the time measured at infinity. At an asymptotic observer in the standard asymptotic time that you have in BMPV, that becomes the PTZ time.
Okay.
And from this here now, I mean really the proper distance for a non-extremal black hole that would be, so the proper distance is exponential in this time, and this is the relation. Now the only thing that I'm assuming here is that if you go to something near extremal, that the time scale doesn't all of a sudden becomes very different because the length of the throat might not change. If it does, then of course the calculation doesn't hold. Right? But if the time scale doesn't drastically change, well, the black hole itself does drastically change because it becomes near extremal, and because it's non-extremal, the distance from the horizon is exponential in the time scale. And this is the relation that Josip was asking for. If you work out these details, horizon radius divided by ADS length times this E gap, this is what you get. It works out. So the N1 and 5 cancels with the square root N1 and 5 here, and then an NP here, and all the dimensionful quantities scale out, and this is what you get. But it really depends crucially on having the same magnitude or the same order of magnitude for the time scale. So I mean, I'm happy to see you point to a flaw in the argument. I just found it a neat observation.
Does it suggest also the energy gap changes when you go from to a non-extreme, or the energy gap stays the same, but the
well,
distance?
if it depends, right? If you think that for a non-extremal solution it should be the same type of behavior, then the energy gap has to jump all of a sudden.
Oh, interesting. I had to think about it. Any other comments or questions?
I ask, it's a bit of a mixture between a comment and a question. So here you've been sort of thinking in the context, very much from the string theory side, the sort of D1, D5P system, whereas of course the original discussion of echoes was really in the context of Kerr black holes. Have you tried to do any analysis using the sort of the ideas of sort of Kerr CFT? And it's why it's a comment as well as a question, and it's because I have a sort of master's thesis on this, trying to interpret the echoes in terms of the CFT description. And thinking again, I mean, kind of related to what you're doing here.
Oh, well, I find that very, very interesting. I have no concrete ideas other than that I also put a master student on similar things this year, but nothing fruitful came out actually. But I was planning on giving it another shot next year. So yes, I would be very interested.
We'll communicate in private. I'll share with you what we have. I mean, so we have some interpretation of the reflectivity in terms of the dual CFT, and some ideas of how you would turn this into a microstate description.
Oh yes, that would be super interesting. Yes.
There might be some problem in terms of practicalities, because if you look at the NEC solution, the near horizon extremal Kerr solution, it's really an ADS2 solution. You don't see the gluing when you do Kerr CFT. This near horizon extremal Kerr is really some ADS2 times some constant size fiber. You don't see at all an the fiber opening up into some ADS3 or into flat space. So solving the wave equation and so on, even if you do it in a capped NEC solution, for example, which is something which Pierre built about 2 years ago, you can do a bubbling solution which is just neck asymptotically in the UV and has some bubbles. Even if you do that, it will be very hard to do the scattering problems, because essentially there's no flat space to glue to. There's no flat space and there's no ADS3. So I think this is going to be a technical issue.
Yes, yes. Well, I'm not sure. What I like about the neck region is, or near neck region, is that you can scale basically the light ring into this decoupling region, which makes it a very interesting system to study, where you have extra features. So you not only have this ADS-like region, but you also have the bump in the potential that just goes in. So there's a lot of nice physics that you can do there. Okay, Marika would be very interested. Yes, thank you.
Any further questions or comments?
Hello, can you hear me?
Yep.
Yes.
Go ahead.
Yeah, I have a question. So
Yes.
this is about reflectivity coefficients and the epsilon.
Yes.
So have you thought about what happens when you take epsilon to zero limit?
Can you be more concrete?
Like my intuition says that it should not matter what boundary condition you impose at the horizon, like purely ingoing or reflecting, as long as you are very close to the horizon, the physics of black holes should dominate.
Okay, let me think. How does it go exactly?
Because the throat is already becoming infinite.
Oh, yes. Yeah, so what's going to happen if you do this? So I swept here a factor that depends on the redshift under the rock, because I didn't want to overload the slides. But there is a redshift, a log epsilon factor that enters here in an exponential, etc. And if you work it out, you can rewrite this, especially the denominator. You can just expand it in a sort of Taylor series in R, so that you see the different terms coming, the different echo terms. And each of them comes with a particular timescale. So what happens when you go closer and closer to the horizon is that you're just, let me go back to here. If epsilon goes to 0, then the distance between ring down and echo goes to infinity. So you still have these echoes, but it's going to take so long that you're not going to observe them. I think this is what happens.
Okay, thank you.
Anything else? Okay, well, let's thank Bert again. And that was a wonderful talk. So thank you, Bert. Good start to the conference. And so we'll get together again at 14:30 or 14:25 or so to get connected, and we'll continue then. Okay. See you soon.
Perfect.
There's a question: should I leave the YouTube running and record for the next hour and a half, or should I do another YouTube?
I think we just nuke it. I don't know.
A new YouTube, maybe.
A new YouTube. It's just good to. Okay, so I'll stop. I'll stop the live streaming on YouTube now, and then another one for the later. Okay.
Okay. See you later, guys.